Okay.
So good
Good
afternoon,
afternoon.
everyone. Okay, I'll just hand
No,
it
go
over to
go
you.
ahead. Yes. Yeah.
Yeah. Good afternoon, everyone. We have gathered here today to give away the ISSS awards for the year 2020, though we are doing it 2021. And we congratulate all the awardees for their achievement. And the welcome address will be now given by the President, Professor G. K. Anand Suresh. So you can do it.
Yeah. Thank you, Veda. Good afternoon, everyone. This is a time of celebration. We've already announced the ISSS awards last month, and today we are going to listen to the talks by all the awardees. And I welcome you on behalf of all of ISSS members and the governing council to this occasion where we get to listen to the wonderful work done by all the people. I must congratulate all the people who were nominated for the awards because the last year, as we all know, has been a difficult year that we all somehow endured. And despite that, we had a record number of nominations this year. So those of you who actually got the awards now should be pleased that there were a lot of nominations this year compared to earlier years, and probably because of online interaction. So there are some nice things that this pandemic has done to us, which is we're able to connect more often in the virtual platform. And that way, I think more nominations have come. And I congratulate all the people who are nominated. Those who got the awards and who will be presenting today are, in some sense, first among equals. So let's actually give a grand applause to all the people who were nominated for the awards, and of course, congratulate those who have won the awards. And even though it's a virtual platform and we are meeting virtually, but the awards are going to be real. Certificates already printed. I've signed them, and they will go to Vidya Shankar for his signature, and they'll be mailed to each one of you. And there'll be cash awards also that they'll be real; they'll not be virtual. And for the Young Scientist Award, there is even a medal that is personally engraved and a citation, which we'll hand over to Professor Hardik Pandya when he comes back from Shimoga to Bangalore. So he's in currently Shimoga on his gate duty. And one other thing I would say, which I just said, is that all of you should consider publishing your work in Journal of ISSS. And so it's going to be indexed in due course in Scopus as well as UGC Care, so that you will also be able to convince your school authorities, college authorities to consider count the ISSS journal. Professor Gopalakrishnan, who is the editor-in-chief and the editorial board, which is now truly international, they're working very hard with two social media editors to promote the journal, so that your journal paper will be given due readership. Because whenever we write a paper, we want it to be read by people, and that's the hard work that editorial team is putting into it. So we should consider sending this to ISSS journal. So without further ado, we would begin with the talk by Professor Hardik Pandya. But before that, I must thank Veda, Sunil, Revati, and our Professor Atre and the past presidents, Professor Vinay and Professor Gopalakrishnan, for guiding us constantly in ISSS activities. And we have a great team with Sudhakar, Vidya Shankar, and Veda doing all the work, and a lot of others helping us. Thank you all for participating in this session.
Thank you, sir. Now I will just go ahead with the schedule that we have. So I will go with the first award, that is the Young Scientist Award. And ISSS wishes to congratulate Professor Hardik Pandya from Indian Institute of Science for his work on biomedical devices and technologies. I will just read the citation and then give the floor to him. So let me just share the citation. Yeah. I hope it's visible to everyone. So the Young Scientist Award, Dr. Hardik Pandya is an assistant professor at Department of Electronic Systems Engineering, IISc Bangalore. Dr. Pandya got his bachelor's and master's degree in electronics from Sardar Patel University in Gujarat and a PhD from IIT Delhi in 2013 with specializations in microelectronics. He pursued his R&D interest in University of Maryland, College Park, US, in the critical area of applications of microsensors and devices for the treatment of breast cancer. Between 2012 and 2013, he worked on the design, simulation, and fabrication of microcantilever and interdigitated electrodes for breast cancer diagnosis. He has also fabricated microforce sensors for measuring catheter contact forces. In 2016, Dr. Pandya, as a postdoctoral fellow at Brigham and Women's Hospital, Harvard Medical School, Cambridge, Massachusetts, USA, was involved in understanding the efficacy of chemotherapy drugs using microfluidics and assessing antibiotic susceptibility using microchips. Continuing this effort at ISC, Dr. Pandya developed several diagnostic tools and devices to assess the malignancy and biopsy tissues, an interoperative probe for brain tumor dissection using MEMS-based sensors, and a mobile platform for screening oral cancers in remote health centers using machine learning. In addition, along with his colleagues from IIC and Indira Gandhi Institute of Child Health, he has developed a portable platform for carrying out rapid antibiotic susceptibility testing using microfluidic devices, thereby reducing the time involved in assessment from couple of days to couple of hours. Dr. Pandya has scores of papers and patents to his credit, and it is evident that Dr. Pandya has developed a strong platform for the understanding and deployment of microsystems in the critical area of biomedical applications with several demonstrated successes. I would like to congratulate on behalf of ISSS Dr. Pandya for receiving this award and hand over the platform to him.
Yeah, thank you everyone. Thank you very much. I just thought that I'm getting old, but getting this award makes me feel younger again because Young Scientist Award at age of 39. So that infuses a lot of enthusiasm and the courage to work more and work harder. So thank you very much, the entire team of jury and the president and the earlier president as well, who asked me to apply. So let me start presenting my work. Okay, so since this award, I think I can, everybody is able to see the screen. If one of you can confirm, it will be really helpful.
It is
Can you see
visible.
this? Yeah, okay, great.
Yeah, we can
You
see.
just click on the hide button for the top bottom one. Yeah.
Yeah. Sure. So, so since the award is given for the work done in India, I'll be only talking about what I did after joining IISc in January 2017, and I'll try to show the applications of the research area rather than going into one topic and going to depth. I want to show the breadth because I believe that that will help the attendees to understand what are the applications of micro and nano engineering technologies for healthcare. So as I said, I focus on microsystems and healthcare technologies, and both we apply for non-communicable diseases and non-communicable diseases. The applications are from understanding the heart tissues as the disease progresses, or for breast cancer screening and diagnosis, for rectal inflammation, for oral cancer, neonatal hearing, brain tumor. We understand the physiology. We understand the cancer delineation in brain tumor. And we also try to develop several biomedical devices for the same. So if I talk about healthcare, right, it is not possible to work in such a difficult area without having a right collaboration. Now, when I say right collaboration, does not mean that only clinicians are right collaboration, but for the healthcare technologists and for the people who are working in this area, it's very important to get feedback from the clinicians. So I was fortunate and I invested a lot of energy in having a right collaborator, clinical collaborators. And you can see here around 20 of those are in front of you, right from neurosurgeons from NIMANS, from Ramaya Institute, to cardiologist and cardiothoracic surgeon from Jaideva, to ENT surgeon from Hubli, to neonatologists and pediatric surgeons from Indira Gandhi Institute, as well as Majumdar Medical Center, physiology from AIIMS. We have oncologists from several institutes, including India and abroad. So these are all the people who actually comes up with ideas. And we as an engineer try to solve and try to put our all the efforts to make it working, one which is a prototype, and then try to translate it at some point of time. So having said that, without having a right students, good students and smart students, I will not be able to talk anything. In fact, a lot of faculty, either in the institute or anywhere in the world, would not be able to do a lot of good things until you have a right team. Right. So all these things that I am showing it today is because of the students that were involved in working on this several areas. These are some of the clean room. Actually, I have two clean rooms in the department, and you can see some of the photographs of the clean room and the tools that are there in the clean room. It is class 10,000 clean room environment. Like I said, I have two labs. One lab is exclusively for engineering, another is for interfacing between biology and engineering. Now, when you talk about medical devices or healthcare technologies, most of time I heard that, oh, you are a biologist, or sometimes you are an electronics engineer, so how you can use it for healthcare applications. So it's very interdisciplinary topic, and it is important to understand several areas, starting from even physiology to electronic system design to embedded systems, a bit of machine learning if you are going to use that, microengineering technologies and analog electronics. So and when you understand these topics, right, it's easier for you to apply it for healthcare technologies. Now, having said that, this technology includes people from different areas of research: mechanical engineers, robotics engineers, electronics engineer, microsystems and design, right, AI guys. So it is very interesting area to if somebody wants to work on. So, and then where we publish. So these are all the publications that has resulted in last 4 years, right from IEEE TBME to T-Biocast to biosensors, lab on a chip, clinical biomechanics. And then now I look forward for also journal of ISSS to see how my research would fit in. I'd be very happy to submit one or two publications in the same. So having said that, let me go to a few topics. Like I said, I'll try to put my talk within 20 minutes. The first topic is on understanding or developing an intraoperative probe from brain tumor delineation. Now you can see here is an actual brain, human brain. And if there is a tumor, it's very difficult for a surgeon to understand where exactly tumor is. So that's why tumor visualization is very important. Surgical planning is very important. And it is known that about 26% of the improvement in the survival is there if the tumor is detected early and can be resected early. So also 3.3 lakh new cases of brain cancers annually, and the incidence is rising sharply. So the point that I'm making here is that when the surgeon will operate the tumor, it's very important to understand tumor boundary. And there is no tool that can like a probe. There is no probe that that a surgeon can use during surgery to understand this tumor boundary. So with that focus in mind, I had a collaboration with IIT Gandhinagar. There are two another assistant professors who are very good in ultrasound imaging and elasticity. And my expertise is on fabrication. So we try to work together, and we have developed a probe. We are actually developing a probe. I should not say we have developed. And then we are trying to see that how our proposed work would be better than the existing technologies, right? One thing is it should be portable, it should be used during surgery, right? And second, it should also compare with the existing technologies. So I have compared a few technologies that are used currently in the surgery, which is brain tumor surgery. So details of technology and methodology. We tried with developing few sensors instead of flexible sensor. I'll show you in few slides. We place it on red brain tissue to understand that if the tumor boundary is there or the tumor is there, how it will be different compared to normal regions. Now in red, it is difficult to create tumor. That's why we create stroke. All right, and this is the UI that we have developed. I'll show you the actual implementation of this device. Now, moving forward, we want to have the MEMS sensors surrounded by electrical sensors to understand the electromechanical properties, or if you want to show for imaging, then electrical and imaging technologies. So with that point in mind, these are some of the work done by the co-PIs. So I'll just skip it. But this is the probe that we have filed a patent. It's a provisional patent. We have 11 months to add the claims to that. And now we are trying to measure the different regions in human brain to see the electrical property, and then later on we are developing a PMUTs or array of PMUTs to see how we can understand the elasticity or imaging. This is one of the example, the flexible devices. These are all 32 electrodes that you can use for measuring ECOG. What does ECOG means? You have heard EEG, right? That is electrodes that are kept on the scalp. ECOG is when you keep the electrodes or implant the electrodes on brain, all right? And it's called electrocardiography. So to understand this thing, we have developed these flexible sensors, and we have implanted this thing inside rat's brain, and then we have to check whether rat is alive, right? You can always do surgery, but what is the success of your surgery? So you can see here that after 4 days of the implantation, there is no side effect. Actually, there is no bacterial infection, and of course, this was done by the surgeon. I got training to operate the rat, but I'm not too sure whether rat will survive or not. So I'll not touch that particular area that I'm not confident of. We use for understanding the immunotherapy. So we used to take spleen. This is all about brain. So we require a specialist. But you can see very clearly that the rat is okay. Now, moving forward, if you want to work on any of this area, if you want to use human samples or animal samples, you have to get ethical clearance. So we have ethical clearance from Siemens. We also have ethical clearance from ISSC to use these samples. Now let me go to the second topic. Like I said, I'll try to put few topics today. The second topic is on neonatal hearing screening. So what happens is that when a baby is born, which are called neonates, right? There is a system called BERA, which is used to understand whether baby can hear or not. Now the system itself is 14 lakh, and only tertiary clinic and secondary clinics, some of the secondary clinics in India has this system. What about villages? I believe that very few or none primary healthcare centers has this system, and that means that when the babies are born in villages, particularly even in some of the secondary healthcare secondary clinics, sorry, they either don't go for BERA, or only when they are 2 years old, the parents would know that baby cannot hear, and that will affect the overall ability of either cognitive ability or the speech and a lot of other applications. So what we thought is to develop a band that you can place on the neonate, and you can immediately understand whether neonate can hear or not. So to do that, we tried to work with a ENT surgeon, Dr. Manjunath Dandi from Hubli, and we have got the funding for the same. So here is the some of the statistics regarding the neonatal hearing screening. And what I will show you a video. You can see here. I think you can hear also probably. Now the early intervention, you see. So the point that I'm making here is that early intervention is very, very important, and timely intervention both. So to do that, there are screening techniques like OAE or ABR, right? These systems are very costly, and that's why we are trying to develop this kind of a band, which is very easy, baby friendly, can be used, and of course there is a lot of research involved. There is a PhD student working on the same. So we are also looking at mismatch negativity, which is only signal which are when the babies are born, particularly because the bone is not fused. That's called bone is not fused. So we are trying to understand MMN as well as the ERP signals. This is a band that we have developed. We have tried with adults, and now we are doing another one for the neonate. You can see in this video that when the person who is wearing the band will blink, you can see a big signal coming out, right? And that is your EMG signal. So these are EEG signals, and whenever there is a blink, there is a other signal, and that's EMG signal. So the point that I'm making is that now this band can acquire EEG and EMG. We have to filter out the signals which were not required. Now she is clenching teeth. We can see very clearly here the signals are changing. The point that I'm making here is that this entire system is made here in the laboratory. For some of the components we have to rely, for example, dry electrodes we have to import, and other things. So these are some of the results from the band. We can see MMN, we can see standard AEP. We are trying AEP also. We are trying P300, which is a positive peak at 300 milliseconds. audio and visual both. Particularly for babies, only audio signals are important, or audio stimulus is important. These are some of the specification of the proposed headband. We are around TRL4 level as of now. We have got ethical clearance to use this band on about 200 neonates. So we are doing the same. Now let me go to another topic, and that is on breast cancer health burden. Now, breast cancer, as all of us know, it is the second largest cause of women-related death or cancer-related death in women. Sorry about that. The early intervention again around stage one will improve the survival. So this is a standard way of how the breast cancer is diagnosed, either physical exam at home or clinical breast exam, which will be done by clinician, followed by MRI ultrasound. If the MRI ultrasound looks suspicious, we have to go for biopsy, where that particular area or breast tissue is taken out, and then it goes for the immunohistochemistry, which they look at the estrogen, progesterone, and HER2 plus minus biomarker, followed by staging and subtyping. Now, what is the problem here? There is no problem actually. But when the surgeon is operating during the intraoperative surgery, the tissue is taken out, is sent to the pathologist, and the person has to wait until the results are back. So, can we develop a system that you can place the tissue and can tell whether there is cancer or not? And for that, we are of course asking a lot of research questions, that whether the electrical or thermal properties of the breast tissue would change with disease progression, whether the mechanical property would change, right? How this coupling effect will help, or is there any coupling between electrical, mechanical, and thermal? So we have developed this system. This is a small chip that you can see here. It's a microchip, and entire electronics is developed right here at IISc. Like I said, this is done by mechanical engineers. The GUI was developed by the software guys. Right? We have developed the microsensors. Of course, when I say this is done entirely by my team, but different students from different field. Okay. So this is a chip that we have fabricated. It has a micro heater, it has thermistors and interdigital electrodes. So what we do is we place a tissue, and when you touch the tissue, if we apply heat on one side, we measure the temperature on the other side, and we can understand thermoconductivity. If we apply a voltage across the tissue, we can see change in the current, and we can measure the resistivity of the tissue. We are trying to see the paraffinous tissue, we are trying to see formalin fixed tissue, and now we are going for fresh biopsy tissues. So students will go to Assam Medical College, with whom we have collaboration, and will use the fresh tissue. Some of the results, we have submitting a paper. We have submitted one paper. This is a second paper that has come. Of course, the manuscript is ready. We are submitting. The point that here you can see is that normal tissues have different bulk resistivity compared to the tumor tissues. Also, there is a difference between formalin fixed and paraffinized tissues. There is a huge difference. Particularly formalin fixed has a better delineation, because in paraffinized they put the tissue in wax, and you have to deparaffinize it using xylene to remove the wax. But formalin fixed you don't have. Of course, we have to do the fresh tissue study to understand how this system works for fresh tissues as well. The importance of this particular topic is to use at a different area, because you can be used for brain tissues as well, oral cancer as well, because when the biopsy is done, the tissue is taken out from the oral cavity. For melanoma, it can be used. For colorectal it can be used, and for cervical cancer also it can be used. Our focus is right now on the oral cancer, brain cancer, and breast cancer. So again, we have ethical clearance from institute, also biosafety clearance to use the tissue in the laboratory. And the advantage of this system is it is label free, easy to use. It can be used in intraoperative environment. That is our what we envisage. We have to do that study further. This is about the ethical clearance. Let me go to one more topic before I stop. Of course, I have several to show. So all of you are free to contact me, and I'm very happy to share all the research areas as well. So this is about smart catheters for cardiac ablation. Now all of us know that our heart beats in a uniform fashion, right? But in a disease called atrial fibrillation, heart starts pumping unevenly. This is because of the misfiring of signal. And the way to correct it is by inserting, either by giving the medicines, or by inserting a catheter. Catheter is nothing but a tube, and when the surgeon inserts a tube, first there is an electrical mapping to understand where the misfiring is occurring. After the electrical mapping is done, surgeon will insert another catheter to burn that area. That burning is called ablation. They use RF frequency, so it's called RF ablation. So catheter RF ablation catheters called RF ablation catheters. Now the point is that when the surgeon will insert the catheter and will touch the tissue to apply the RF frequency, right, radio frequency, then what will happen? If the force is more, the other area of heart will burn. The force is less, recurrence will occur. So it is very important to understand the catheter contact tip force, and also none of the catheter has haptics. So we're trying to add haptics to it so that the surgeon will also feel the force along with looking at the force. So these are another student of mine, PhD student, is working on this microforce sensor. We're developing a tip of the catheter, and then finally we want to integrate with the existing tube and study. To study this, we will use the pig's heart, and recently we have got the ethical clearance from Jaideva to use human heart. Of course, we are not going to do in vivo testing for now. Maybe the next student will continue that research, but my current PhD student will continue or will work on using the pig's heart and using the ex vivo human hearts. Ex vivo studies using the human heart. So again, this is a design of the catheter, and you can see that we have our focus is mainly on the tip of the catheter, and of course the electronics associated with it. So these are some of the work that he's doing. There are a lot of results, but just to quickly finish it, we have ethical clearance to work on this particular topic as well, as you can see here. Yeah, I don't know about the time. If there is 2-3 minutes left, I can take one more topic. Veda,
Yes,
is it
yes, you
possible?
have. You
Okay, I
have.
have 5 minutes.
Yes, you have 5 minutes.
Oh, great. Okay, I'll talk two topics then. Okay, great. So there is a bioresorbable chips that we are working on. So these are implantable chips. Okay. Now we know that there are biocompatible chips, right? Or biocompatible materials. What are bioresorbable materials? That means that once you implant the chip will dissolve in the body or absorb in the body. That means that the surgeon doesn't have to do again surgery to take it out. Now, this has been done and led by several groups. Particularly, John Rogers started this area as far as my understanding goes. And you can see all these papers coming out of his group. Either his postdoc who joined as a faculty and they continued this work. So the fortunate thing is that we know a lot of materials from the publication. The another point that we have seen that they have tried for several applications, right, to understand the intracranial temperature and pressure, to understand the EEG or ECOG, like I said, and then there are flexible sensors, flexible materials that are used to measure the same ECOG signals. You can see here that this is a basal signal, and then when you add penicillin, and penicillin will cause the epilepsy. Epilepsy is nothing but fit, and you can see here seizure. Right after 4 minutes to 6 minutes, the seizure occurs fast. Now, what does this chip doesn't have? This chip doesn't have the way to understand the efficacy of the anti-epileptic drugs. What is efficacy? Efficacy is the usefulness, effectiveness. So we have developed a chip with three holes you can see here. This chip, these are recording electrodes, these are contact electrodes. This recording electrode will measure the signals, ECOG signals from the rat's brain. We can create epilepsy by using bacillin or penicillin in the center. When we load the anti-epileptic drug from the two holes on the side, we should be able to see whether the drugs are effective or not, and whether we can receive the basal line or not. This is the proposed plan. Now we are going to fabricate. We already fabricated it. We tried these bioresorbability studies, and we were able to see that for 12 days the chip works very well. After that, it starts dissolving. We have tried the artificial CSF, also human CSF. This work is along with Niemann's, and these are the chips that we have fabricated. Again, ethical clearance is there to use the rat for understanding epilepsy and stroke. This is my last topic. Since I had 5 minutes, I think I took 2.5 minutes. So this is for the steerable intubation catheter. What happens is that when the child is or the children are in the hospital on ventilator, sometimes it causes their trachea to inflame. Trachea is a windpipe. Now, if inflates or inflammation is there, what will happen? That the child will be having a difficulty while breathing, right? So then, as far as my understanding goes, again from the pediatric surgeon, that there is no tool that you can place like a catheter and you can measure the flow rate and also tell where is the stenosis. Stenosis is the area where there is a trachea is inflamed. So we are trying to develop such kind of catheter, and you can see here that is only a costly system like CT scan or conventional bronchoscopy are used. There are certain statistics, there are certain pros and cons. We are developing, so you can see here this is how the surgeon will be using it to understand the inflammation, right? And we are trying to develop a series of micro heater that can be integrated on the catheter. Also, there is a force sensor at the tip, and we are again trying to see whether we can measure the elasticity of the tissue. So this is a small setup that we have tried. Here we are using SIP trachea. So SIP is used because it's easy to get these samples. And we clean the trachea, we float it, and then we inflate and deflate the bag, which you can see on the right side, which will work like a test lung. And then we measure how effective our catheter is, integrated with all the microsensors. So see, these are some of the results we have submitted in GMM. The manuscript is in revision, and we hope that it will be accepted. And then there is a second phase of this study and third phase. We are at preliminary stage of this study, but we are excited that these all things are moving forward in the right direction. Again, I thank clearance. So I'll stop here before moving to other topics. Once again, I'm very happy, and I thank all the committee members to give me a chance, an opportunity to share my work. I look forward to continue this topic, and I want to make sure that some of these topics translates and it will help humans. It will save some life, but at least help in screening and diagnosing the diseases. Thank you very much.
Thank you, Professor Pandya. That was really wonderful, and to see the kind of work you have done, and we really appreciate and hope the audience here comes forward and joins you in this research. If they have some questions, they can always contact him later. Also, I don't see any questions put up, so I'll
Sure,
go to
sure. They can ask me anytime. My name is very easy to remember, right? Those who like cricket, they can remember my name, and I will definitely answer your queries if any. You can always contact me via email. Thank you very much.
Thank you, and congratulations.
Thank you.
So, moving ahead, we have the next awardee, the PhD student award. The winner is Dr. Nishant Kumar of Indian Institute of Indian Institute of Technology, Delhi. And it is for his work on smart power grid system, integration of solar PV with low voltage weak grid system. And he was supervised by Professor Bhim Singh, and we congratulate both of them for this award. I now request Dr. Nishant to take over the stage.
Thank you, ma'am.
Yeah, please go ahead.
I think my screen is visible to everyone.
Yes.
Yeah. Okay. Before going to start, first of all, I'd like to thank the ISS Award Committee jury members for selecting me for this award, as well as I also like to thank the organizing committee members for this beautiful session. And today's my topic, which is based on my PhD work, is a smart power grid system. In this work, mainly I have worked on the grid integrated solar PV system. This is a very known topic in the field of energy, mainly in the renewable energy area, and also in the suppose when you will think about Indian prospects, and now Indian government is also continuously targeting and putting money on solar. So solar is nowadays popular as a renewable in India. Definitely in Europe side, the wind is most popular, but in India, this solar is the most popular one. But few challenges is here in Indian constants. So I have tried to target both those topics, those problems. The few problems is in this system is first is the partial shading problem, means due to the heavy dust layer or due to the shadow of any building, tower, tree on the panel characteristics deteriorated. So on that time, how we will track the maximum power? This is the one of the challenge. Another is that this solar panel and converter and everything, means we can say the solar power generating system mainly works in the daytime, and we know that this daytime is only for 8 hours. Suppose we are thinking about the solar radiations, means morning 8 to evening 4, around like that, and after 4 the solar radiation is very lesser, right? So for this system works only for 8 hours, or maximum 9 to 10 hours we can say, but rest 12 hour or 16 hour, this whole system is useless. So is any way so that we can use this system in this other time? Definitely that time solar will be not there, but for other purpose we can use this system. Definitely we can use. So I have tried to incorporate that thing also here. So that is one of the another things which I have added here. And third one is the control side challenges. Control side challenges is that in India, majority of converters are coming from the developed country. Developed countries means we can say the US, Europe, or China. Majority of converters are coming from there. And when you will think about the grid conditions in these developed country, their grid is very stiff, or we can say the grid power and power qualities are very good with respect to Indian climate. But due to this, the power quality issues are that converters are not capable to handle that power quality issues which are in India, as well as we can say the dynamic conditions which are in India. So that thing also I have incorporated. So these three things I have tried to mitigate during my PhD work. So for that purpose, mainly I have developed a highly robust control technique and tested those technique on hardware setup in Indian climate. So that is the main goal of the whole work. In this is on this screen, I have shown the main circuit, the circuit in a practical way. In this circuit, you can say this one is the solar panel. I think my laser is visible to everyone. And this is the two converters I have used here. This is one converter. This converter is DC-DC converter. We can say this is a boost converter, and this is the DC to AC converter I have used, because we know the grid is AC as well as majority of our load is AC. So I have used here DC to AC converter, and two converter back to back are coupled. And these two filters I have used. This is a one RC filter, and this interfacing inductors I have used here. And in this system, I have not used battery, because we know we are not that much rich, and as well as this panel is already costly. So when we will use that battery here, so then cost will increase in a significant way, as well as maintenance is also another task with battery. So here the main goal is that this grid, universal grid, or we can say the national grid, we will use for two-way, the sink and source, like that we can say, means that when our load is when our generation is more than load, then extra power we will fed into the grid. And when our load and generation is load is higher with respect to generation, then we will take extra power from the grid. So here we will use grid as a source and sink. So for that purpose, grid is integrated here, but no battery has used here. So this is one good thing in this system. So for that purpose, two control technique I have developed. One is for DC-DC converter, and this control name is learning based incremental conductance algorithm. And the main target of this algorithm is to track the maximum power on the PV converter, in PV panel. Because in this PV panel, whenever any shading will occurs, or whenever solar radiation will change, then maximum power point changes. And when maximum power point changes, then operating points also changes. And we know that the panel efficiency or panel efficiency is very lesser. For example, in practical panel, 20 to 22% is the efficiency of this panel. And in these situations, if we are not able to extract that 22% of power, then this efficiency will further go down. So here that extraction of that 20 or 22% of power is also very important. So for that purpose, I have developed this learning based incremental conductance algorithm. And this algorithm finally generates the duty cycle. This duty cycle is for what? For boost converter, and boost converter means DC-DC converter, which is coupled with this panel. So that main goal of this algorithm is track the panel conditions, or we can say track the solar radiation condition, and accordingly decides the operating point, and operate on a maximum power, or we can say the peak power. This is the main goal of this algorithm, which I have developed here. And another is that grid integrated system, means VSC I have used, a grid integrated voltage converter I have used. And for that purpose also, again, a robust control is required, because that control will convert DC to AC and try to match all our expectation, the key expectations, like the power quality. Power quality means when we will convert DC to AC, then that power quality of the AC side is more and more pure, or more pure means more and more sinusoidal. So that is the one challenge, or our expectation. So for that purpose, this control is very important. Another one is that definitely I have included the load on the PCC, or PCC means on the output side of the voltage source converter, and that load is household load, or which are mainly nonlinear in nature. So when these loads are nonlinear, then definitely the non-linear loads will extract nonlinear currents. When this load will extract that nonlinear currents, who will generate? Then definitely this converter will generate that nonlinear currents. So if this converter will not generate, then definitely load will take, but that time that load will take that current from the grid, and that extra burden will come on the grid. So this converter generates that nonlinear currents according to the load requirement. So here the key challenge is estimation of this nonlinear current requirement, because when the this converter will generate more nonlinear currents, then load will take according to the requirement, but extra will go in the grid, which is also not a good thing. Another way is that if we will generate lesser with respect to load, then load will take again fix, but load will take extra from the grid. So in both conditions, grid will take or grid will give nonlinear current, so which is not a good or good practice. So here that matching is very important, so that this converter will generate exactly equal to the load demand. So this is also one way, one important thing. So for that purpose, here I have developed one filter, normalized Laplacian kernel filter. This filter extracts the major informations from grid. So what type of power and what amount of power load is try to extract from the source. So and according to this informations, this converter operates accordingly and generates that much of power. So this is the main thing here. So for that purpose, I have developed this filter here, and what I have shown the maximum power point tracking means learning based incremental conductance, that is here, and this side, this incremental conductance generates the Vref, and according to the required Vref, the duty cycle is generating, and this duty cycle triggering the DC-DC converter. And this side, according to this, we generates the current reference, and according to the grid current, actual grid current and current reference, we generates the switching pattern for voltage source converter. So this is the key thing here. And but in the whole operations, this filter is a very important normalized Laplacian kernel adaptive Kalman filter, because this filter had two key work. The first one is that extraction of active and reactive, or we can say linear or nonlinear current requirement estimation of the load. So this filter tries to extract that information. Another one is that in this system, I have not used PLL. PLL means phase lock loop system, means that for grid synchronization, in general practices that use the PLL for find the theta, and according to the theta generates the current for grid synchronization. But in this system, I have not used that, because the dynamic performance of that PLL, that type of system or that type of control is poor, because when the grid voltage goes up and down, then accordingly that theta also not go up and down with that speed. So for that, so in that situations, the voltage lag occurs on the PSC.
Dr. Nishant, you have 2 minutes.
Okay, sure, ma'am. So this is also important, which is by using this filter, I have tried to match that. So what controls I have developed, that control I have tested on the experimental setup. This is the experimental setup where I have implemented that control, means both control, DC-DC converter and DC to AC converter, control both. So you can see here this system. So both converter is here, boost converter and VSC both converters are here, and all the sensors are here. And on the place of PB, I have used the PB simulator here, and this is the grid, actual grid I have considered. This is the Indian grid conditions here, and the processor is here. So, and this is experimental results, and in this experimental results, I have taken the nonlinear loads. In this nonlinear loads, also load unbalance conditions also I have taken, and you can see how the grid currents are more sinusoidal, which is the main challenge. And see, the loads are highly nonlinear, but grid current is very pure. So also this is the harmonic analysis of the whole system, and this harmonic analysis shows that the TSD is 1.9%. This is very good according to the situation. Also, I have gone through the solar radiation's fall conditions, how the solar radiation is changing, then system is working. Similarly, solar radiation rise conditions, and see the efficiency. This is 99.97% and 99.98%. This is MPPT efficiency. This is not solar panel efficiency. Means how purely I am able to extract that power. That efficiency I have shown here. Similarly, over voltage means grid side some issue is that grid voltage has gone up, grid voltage has gone down. Then how system is working. Similarly, voltage unbalance. So voltage has unbalance. All three voltage unbalanced, but still see currents are very balanced. Currents are very pure and similar. So this is the key challenge. Also see the current unbalance is 0.2%, but grid voltage is 32% unbalance in the voltage side. So this is the objective of the whole work. Similarly, grid voltage distortion conditions, grid currents are pure. That is this is the system. And the last point is that day to night mode of operation means that in the daytime our solar system is working as a grid integrated solar PV system, but in night time, this definitely sun is not there, but in night time we can use that system as a D statecom. Means that the converter and capacitor will generate the reactive power for the support supports the grid, or we can say generates the nonlinear currents for load in night time. Means that we can say the grid supportive mode in the night time. Similarly, in the night to day mode also, means in the night how the system is working in it as a D statecom, and daytime it works as a PV grid integrated system. This is the very unique point here, and automatically this thing is happening. No manual work is here. System automatically change according to the time, according to the situation. And then finally, I can conclude that the one learning-based MPPT and as well as VSC control I have developed in this work for grid integrated system in Indian climate. Means I have chosen the weak grid system especially for that. So these are my publications which I have shown here. Thank you for your kind attention. If any questions, I prepare that.
There's nothing posted, so I'll ask people to put it on the chat box. And thank you, Dr. Nishant, and congratulations once again for this work.
Thank you, ma'am.
So you can unshare it
Yes.
so that I can share the next one. Thank you. Yeah, we go to the next set of awards. The first runners-up for the ISSS PhD Student Award goes to Dr. Poonam Sundriyal from IIT Kanpur for her work on fabrication of nanoscale materials and surfaces for energy storage devices and adhesion bonding applications. She has carried out her work under the supervision of Professor Shantanu Bhattacharya. ISSS wishes to congratulate both of them, and I request now Dr. Poonam to take over.
Thank you, Dr. Veda. My screen is visible to all of you.
Yeah, now it is.
Okay. So good afternoon to all of you. So at the outset, I would like to thank you, and I would like to thank the selection committee and ISSS team for selecting me for this award and for providing me an opportunity to present my work in this platform. So during my PhD, I have developed the printed supercapacitors and batteries for flexible and wearable electronic applications. So as we all know that right now, our country is dependent on the foreign market for the different electronics devices and as well as to the energy storage devices. So my goal here was to develop my goal was to improve the manufacturing capability of our country so that we can be self-dependent for our energy and electronics need. So starting from the flexible energy storage devices. So as we all know that flexible electronic devices have recently emerged as a potential solution for the next generation electronics. However, the traditional devices and traditional electronics has the rigid feature, and therefore it is not compatible with the next generation electronics, which has flexible and wearable features. So we really need to work in this area, that how we can develop the high performance and flexible devices for different applications. And energy storage device is one of the main component, and my goal was mainly focused on it, that how we can develop the flexible batteries and supercapacitors which have the various features like bendability, rollability, and foldability and other features, so that that can be used for the portable, compact, and other electronic devices. So if we will see the technology status of the different flexible electronic devices, that we can see here, that especially this in the transport and renewable, it is still in the initial stage. In some of the applications like smartphones and the wearables are somehow customized, but however they are just the miniaturized devices and they are not completely flexible. So in order to increase their application potential, we really need to work in this area. And if you will see the plot here, that then we can see that the right now our batteries and supercapacitors don't have the enough energy and power densities that can be power the next generation electronics. And especially in the renewables, right now our government is installing huge plants for the solar energy. However, one of the main challenge is that how to store the generated energy. So we really need to work in the energy storage devices as well. Here, if you will see the technology roadmap, that we can clearly see that since the year 2013 to now the various features are now added to the rigid electronics like bendability, foldability, and others. And in the coming years, we need to increase its features so that it can be used for the different applications, especially for the wearable applications. So during PhD, I have uh, tried to solve the different research gaps of the supercapacitors and batteries. And one of the main gap is that was the poor scalability, which was mainly due to the use of the traditional fabrication methods. So I have tried to use the smart manufacturing method like inkjet printing. This inkjet printing is the CAD drawing based manufacturing, where we can easily change the shape, size, and features of the of the designs or the patterns just by using the CAD drawing. So I have used it so that we can uh, use the make the devices with different shape and size, and we can also improve their design. The other problem is that the existing and the traditional devices are incompatible to the flexible electronic devices due to their rigid feature, their heavy weight, and their high cost, and the use of the aqueous electrolyte. So I have tried to use the paper and textile as the substrate for the development of super flexible supercapacitors. And I have also optimized the device parameters and the different designs so that we can get the better performance. One of the major problem is the generation of the electronic waste of the existing devices. So I have tried to use the paper, textile devices, and biodegradable components so that we can reduce these electronic waste, and we can even make the zero waste electronics. So with this much of introduction, now I want to move forward to my own work. So my methodology was first for the material selection. So in my material, I have used a graphene and graphene oxide as main material for the printed electronics. Then I have prepared the inks and optimized it. I have developed the printed electronics with the help of drop-on-demand printers. So one of the major challenge of the drop-on-demand printer is that the inks need to be in the suitable in the optimized range and its density, surface tension, and the viscosity should be in the proper range, so that it will be there will be the quality printing. So I made the inks by using mixing and sonication method. These inks were highly stable for the several years. And as the ink was ready, then I filled them in the ink tank of the printer and developed the electrode patterns and the as well as the supercapacitor and battery patterns with the help of CAD drawing, and then assemble them in the sandwich and planar configuration and check their electrochemical performance using the different tests like cyclic voltammetry, galvanic charge discharge, and electrochemical impedance spectroscopy, and then check their performance by glowing the LED from them. So during my PhD, my first curiosity was that how we can convert a normal A4 paper to a conducting matrix or to a high performance supercapacitor. So for that purpose, I have used the graphene oxide as the ink, and then that has converted this paper to a highly conducting matrix. It has a sheet resistance of only around 0.4 ohm per centimeter square, so which was comparable to the silver and gold coated substrates. And then I have also printed the energy storage material over it, and then with the proper optimization of the different printing layers and by optimizing its electrochemical performance, I have developed the paper based supercapacitor, and it has the excellent flexibility, and it was able to glow the various LEDs from them. So my first step was the material selection, and I have also optimized its physical properties. So this form number was within the range of 8 to 10. And these are some of the electrodes that is printed by using the drop on demand printer. And here we can say that we are able to print the electrodes with different shape and different size. It is one of the print with the help of the graphene oxide ink, and here this figure shows that this sheet resistance was very less with around 40 number of the printing layers. So we have also checked its electrochemical performance, and we have seen that it has an excellent electrochemical performance. It was able to it has a very good lifetime, which has more than 90% of the capacitance retention even after the 9,000 cycles. And our device has the very good energy and power densities as compared to the existing literature in this area. And one of the beauty of such structures that we can easily dispose them by the burning process, and we can again reuse this carbon for the other applications. And it was able to glow LEDs for around 11 minutes. So this is one of my first work in this area. I again tried to develop the fully printed and planar supercapacitors. Here I have used the interdigitated electrodes instead of using the sandwich configuration. And here I have also used the water-based ink, so it was more environment friendly. And after optimizing the various geometrical parameters and thickness, uh, I have seen that it has a very good electrochemical performance, and these devices has a very good energy and power densities. And this device is able to perform in different flexible conditions. Here, I want to show you one of the video which shows that this printed printed supercapacitor on this paper with the 4x4 array of these supercapacitors. It was able to glow an LED, and it was able to glow in even in the different deformation conditions, like in different folding and even in the rolling conditions. So this was my work in the area of the paper-based supercapacitor. So by using such a supercapacitor, we can reduce the cost as well as the waste of the electronics, and we can extend this process for the development of other printed electronics. After this work, I have also developed some fabric-based supercapacitors where I have used the bamboo fabric as a substrate, and then developed the
Dr.
supercapacitor
Poonam,
like
you have
battery.
2 minutes.
Okay, thank you. And then developed these battery supercapacitor hybrid energy storage devices on bamboo fabric, and it also has a very good electrochemical performance, and we were able to use it for the wearable electronic applications. And it was we can also develop the other wearable electronic devices by using this approach. So I would like to acknowledge, I would like to thank my PhD supervisor for the completion of this work. And I'm also thankful to IIT Kanpur and Department and DST for the completion of this work. And the funding organization, Department of Science and Technology, and Boeing for the development for the funding of this work. This work was ranked at TRL 6 level by the Department of Science and Technology, and they are also providing the next funding opportunity for our to our research group under the Atmanirbhar Bharat scheme, and the CMERI and CMET Trishur are already using this technology for the development of printed supercapacitor for some of the application. And Boeing is also using this technique for the development of some of the energy storage devices for aircraft applications. And I'm also right now I am working on the commercialization of these devices. So I would like to thank you for want to thank you for providing me an opportunity to present my work and for considering me for this award. So if you have any questions, you may please ask.
I don't see questions on the chat box, but thank you for presenting, and it's a wonderful work, and congratulations once again.
Thank you, ma'am.
You can stop sharing. Yeah, thank you. So we'll go ahead with the next presentation, and we have the second runner-up award in the PhD category, and the award is given to Dr. Debanjan Acharya of Indian Institute of Engineering, Science and Technology, Shibpur, for his work on highly efficient gas sensor devices based on binary hybrid junctions of semiconducting oxide nanostructures and reduced graphene oxide. He has carried out the work under the supervision of Professor Partha Bhattacharya. ISSS congratulates both of them, and I hand over the stage to Dr. Debanjan. Please share your screen.
Yes, just. Just a minute.
Are you not able to share? Okay. Yeah, it's coming up now. Yeah, we can see it. Please go ahead.
So I am Dr. Debanjan Acharya. Yes.
Please make it full screen. You can go in the PowerPoint mode.
Yes, yes. I am Dr. Debanjan Acharya. First of all, thank you for the jury member of ISSS.
It's still not in PowerPoint mode. Can you make it PowerPoint mode?
Yes, I did. It's PowerPoint mode. Is it visible?
It's visible, but not in the PowerPoint mode.
Okay.
Go into the slide mode, please.
Yes. Is it right
Yeah,
now? Is it
now
okay?
it's fine. Now
Okay.
it's fine.
Thank you. Thank you very much. Thank you very much for this award. I am Dr. Debanjan Acharya. I did my PhD under the supervision of Dr. Partha Bhattacharya from Department of Electronics and Telecommunication Engineering at IIEST Singapore.
Presently, I am associated with EC department, Triple IT Ranchi, as a faculty member. So after coming 10 minutes, I am going to discuss on highly efficient gas sensor devices based on binary hybrid junctions of semiconducting oxide nanostructures and reduced graphene oxide. So this is the content of my talk. First, I will discuss the importance of as alcohol sensing, then what are the limitations of existing technology, and in the following section, I will discuss the methodology adopted to overcome the issues and all the result I have achieved after the fabrication of the different gas sensor devices. So here now, with a few minutes, I want to discuss on the importance of alcohol sensing and the limitations of existing technology. Before going to that, so how can alcohol be sensed? There are several methodologies and the techniques are there, but in this case, I have considered as a gas sensor or the volatile organic compound sensor as a alcohol to sense the alcohol. So first, someone asked me, what is the gas sensor? Gas sensor is a device where resistance of the sensing layer changes in presence of reducing or oxidizing vapor. So here the alcohol is a kind of reducing vapor. So it can, to the exposure of alcohol, the device resistance, very simple. If I go for the resistance only, the device resistance may change. Apart from the conventional uses, alcohol vapor in exhaled breath are recently being used as a potential biomarker for point of care diagnosis of critical diseases like a metabolic disorder, enzymatic disorder, and breast cancer. For example, you can see you will find the methanol in the exhaled breath of a metabolic disorder having the patient having a metabolic disorder. But for these applications, room temperature, I mean very low temperature, highly sensitive, fast responsive, and low concentration that is specifically in ppb level detection is needed. But commercially available alcohol sensor lacks these specifications because this commercially available alcohol sensor suffers from the problems related to the high operating temperature. Very often you will find that the most of the commercially available sensors are operating at high temperature that is around 300 degrees Celsius. So therefore, high power consumption and as a result, unreliable long-term stability. Also, we have observed that the sluggish response time, say for example, for several minutes, 15 to 10 minutes, it will require to sense a particular species or target species. Also, in addition, we have also found the poor selectivity towards particular, particular alcohol or the target species. When it is there are several interfering species surrounding it in it. So the methodology adopted to resolve these existing technological constraints are as follows. So we have done two steps. First step, the most promising one directional and the three directional nanostructures, that is nanoflowers, that is 3D, and the nanotubes, that is 1D of JDNO and TiO2 titanium dioxide were chosen as a basic sensing matrix. That is the pristine structure of these two as a basic sensing matrix. So there are several advantages are there for these one directional and three directional structures. So in the next step, what we did that we have chosen different hybridization and element to enhance the gas sensing characteristics like response time, recovery time, operating temperature, and the response magnitude. So first, what we have done that is the very general and the very well-established procedure to introduce different nanoparticle, that is catalytic nanoparticle. and we have also familiar with the spillover effect of this kind of nanoparticle. So first what we have did, we introduced the palladium nanoparticle, and we have observed the higher response magnitude at the low temperature than that of the pristine nanostructure based alcohol sensor. But we have also observed that due to the long-term exposure of alcohol, the stability and the reliability hindered. So why? Because of the palladium forms the palladium hydride due to the long-term exposure to the alcohol. So we are finding the next solution for this. So eventually, a novel approach of using reduced graphene oxide as a secondary hybridization element is adopted in next step. So why RGO? RGO because the reduced graphene oxide is a molecularly level thin 2D material. So every atom is surface atom. Having said that, so I can use this RGO as a very promising sensing element, the gas sensing element, because the gas sensing phenomena is a surface phenomena. So the introduction of the RGO can, on top of the metal oxide sensing layer, can enhance the sensing characteristics. Not only this, the RGO offers very high carrier mobility, and therefore fast test detection probability in terms of response time and recovery time can be achieved. So our goal was to deposit the RGO on top of this pristine structure, and we have deposited the reduced graphene oxide in form of distributed island on top of the metal oxide nanostructure matrix, and it forms a high mobility connectors between electrodes, that is the measuring electrodes. Now this is the flow chart of my research work during the PhD research work, and first you can see I have developed the different nanostructure by the synthesis. I have synthesized this structure, and then from the pristine nanostructure, first the structure was hybridized using palladium nanoparticle, and in second step by using the RGO reduced graphene oxide layer. So to confirm the presence of the hybridization, we have also followed the rigorous characterization process like FECM, XRD, Raman spectroscopy, and XPS. So we have confirmed the presence of RGO and PD structure and all the other constituents by using this characteristic. In following steps, we have fabricated our devices and take the data and optimize our sensor structure. So here you can see the right one is the package device structure, and this one is our sensor device. So here is a glimpse of our device development and the characterization. Here you can see the several device schematic of hybrid. I mean, these are the hybridized device structure, and a very simple device structure is followed to see. That is a planar structure you can see, and from the FECM image you can see that on top of the, for example, this image, this left image, you can see there is on top of the Jadeno nanoflower you can see the palladium nanoparticles, which is of the size of a palladium nanoparticles is about 5 to 10 nanometer in the range. And in the right column you can see the transparent RGO layer. Here you can easily see the underneath TiO2 nanotube layers, which is below the RGO transparent layer. Here you can see the TiO2 nanoflower layers. Here you can see the Jadeno nanotubes layers, and here you can see the Jadeno nanoflowers. By using Raman spectra, also D and G, these peaks are confirms the presence of RGO in this hybridized structure. So these are the resultant discussion. What we did, we have made a comparative study in
Dr. Debanjan, you have 2 minutes.
Okay, so these are the comparative study we have made. From here, what the conclusion or the thing we have made is as follows: that the the device, the first device, that is the RGO hybrid junction. That is kind of device where we have observed very high response magnitude towards ethanol, and that the performance was explained by using the band diagram. For example, the ethanol sense response magnitude at the 700 ppm was around 605%. And the second device, that is the RGO TiO2 based TiO2 nanotube based device, where we have find the due to the formation of H hole layer, and we have also tailored this H hole layer to control the selectivity towards different molecules. So, and we also observe very high selectivity towards methanol. For example, if you see, if you see this, if you see the HR tape image of this RGO layer, here you can see the hole. These holes are actually act as a molecular filter and introduce the molecular sieving effect. So what does it mean? That, for example, so I have three target gases like methanol, ethanol, and 2-propanol. And we know that the molecular size of the ethanol is lesser than that of molecular size of methanol is lesser than that of ethanol and 2-propanol. So therefore, if we have tailored this H hole size by using the by varying the voltage of the electrodeposition voltage during the deposition of RGO, and we have observed, we have made this hole such that by using this hole, the methanol can only penetrate and go through the can reach to the main sensing layer, that is our TiO2 nanotube layer. So here in this hole, the methanol can penetrate and reach to the TiO2 nanotube layer. So therefore, in this way, we have achieved very high sensitivity as well as the selectivity towards methanol. So these are the conclusion of my work. So here, compared to pristine oxide, its binary hybrid structure using palladium nanoparticle offers superior sensing performance. Among all the palladium hybrid binary structure, palladium 0 nanofibers offered little bit of moderate sensitivity towards methanol. But in case of RGO semiconducting metal oxide structure, we have observed remarkably improved sensing performance by tailoring the H hole size on top of the RGO layer. And we have also obtained very fast response time like 18 seconds, and the recovery time around 26 seconds at room temperature. And we have also attained 62 ppb level detection, that is the lower limit for the methanol detection. And so these are the list of my publication. I have published 12 SCI journals and 11 conference paper. I have a Google service right now till date 334. And among the list of among the SCI journal, I have several IEEE transactions like instrumentation, measurement, nanotechnology, sensors journal, and electronic device lateral sensor actuators B. Thank you very much for giving me the opportunity to present my work in this session.
Thank you, Dr. Debanjan. It's truly a great work, and we congratulate you once again for this achievement.
Thank
so
you.
We'll go ahead. Yeah, if there are questions, it will be put up on the chat box and can be answered. So going ahead with the next presentation. We have the PG awards now. So the PG award for the year 2020 goes to Ms. Pavitra B. of Nitte Meenakshi Institute of Technology for her work on design, development, fabrication, and testing of low-cost laser-engraved embedded nanocomposite-based pressure sensor. She is carried out under the supervision of Professor M.M. Nayak from IISc Bangalore and also Professor Smita Prabhu from Nitte Meenakshi Institute of Technology. ISSS congratulates the whole team for this great work. Now I request Ms. Pavitra to share the screen and start the presentation.
Hello, ma'am. You can see the
It's
presentation.
coming up. Yeah, we can. You can go on the full screen. No, now it is not visible. Yeah, now you can go on the full screen mode.
Now, ma'am.
Yeah, now you can. Thank you.
Hello, everyone. I'm Pavitra. In this occasion, first I would like to thank Founder President Professor V.K. Atre, President Professor Anand Suresh, and all the executive members and members of the ISSS, and Professor Veda for support and coordination. Thank you for selecting me for the award. And I also thank Head of EC Department NMIT and my guide Professor Smita for her support and um, guidance for my entire project work. I also thank Professor Manjunath Nayak for giving me an opportunity to my project work in Science IASC for his support and guidance in my entire project. And finally, I would like to thank all the members of Advancements Packaging Lab for all their support, help, and encouragement. Today's my presentation is on design, development, fabrication and testing of low-cost laser engraved embedded Argeo nanocomposite based pressure sensor. These are my outlines. We are going to talk about introduction, design and development, how is the process and methodology, performance characteristics and results, and conclusion. In introduction, we are using various type of pressure sensor. Uh, the pressure which is converted into electrical output for the measurement, controlling or for recording. So normally we are using the strain gauge. In that metal, semiconductor, thin film, thick film, nanocomposite also we are using. So in these type of pressure sensor used in different applications like automotive, domestic, biomedical, aerospace and defense, mainly in aerospace and defense. So for the measurement of pressure, water level, altitude, airspeed, etc. So in this novel low-cost pressure sensor, we used a new technique, laser engraved on the top of the stainless steel diaphragm, and which is embedded with the Argent nanocomposite as a strain gauge bridge, which is successfully designed, developed, fabricated, tested, and characterized. So here we are not used any expensive process of clean room facility or raw material like silicon wafers, chemicals or packaging tools as well as characterization tools like SEM, XRD or probe station. So design and development of graphene nanocomposite pressure sensor, which is a very low cost sensor which designed, developed and fabricated and laser engraved, after that embedded and made the pressure sensor. So as you can see in the uh, picture, so we on the top of the diaphragm we laser engraved and made the V-stone bridge. After that, you can see in the third figure that Argeo nanocomposite is embedded on the top of the diaphragm. So these Argeo nanocomposite first synthesized and fabricated using the modified hummus method. So when you apply the pressure on the diaphragm, it will happen, deformation will happen, and which causes the tangential and radial strain. This strain converts the change in resistance, and this change in resistance which is proportional to the applied pressure. So methodology. So graphene material is synthesized, fabricated using the modified hummus method. So selecting the stainless steel material, after that after that fabrication will done. So laser engraved on the top of the diaphragm using the AutoCAD mask. So we carried out the Perlin coating to form an insulation on the diaphragm. After that, we drop cast the ink to make the screen print and embedded the on the top of the diaphragm. So to make the electrical connection, we took the lead termination using the silver epoxy. To sense the filming protection using the again doing the uh, Perlin coating. So we used dead weight hydraulic dead weight calibrator. So um, uh, sorry, we tested the device on that and calibrated the sensor by applying the 5 ascending and 5 descending pressure. So we noted down the voltage on the DVM. After that, we integrated with the electronics and packaged the device and prepare the calibration chart according to that one. So around 3-4 times we will do the calibration because to check the repeatability, stability and everything. So after that, we will prepare the specification and user manual for the device. So these are the test setup where we mounted the device on the dead weight calibrator. So in this one we can calibrate up to 1200 bar, but I calibrated for 20 and 40 bar maximum, and we connected to the power supply and device is excited for 5 volt, and we noted down the voltage using the DVM. So these are the test setup. As you can see here, device is there. So performance characteristics and result. Uh, we applied the pressure 20 and 40 bar to the sensor and with the 5 volt excitation. So when pressure is applied for the device in a 5 ascending and 5 descending order, we noted down the voltage output voltage. So we got a linear output for a pressure versus voltage for both the sensors. So we calculate the zero offset full scale output sensitivity, non-linearity hysteresis using the least square method. So as you can see in the table, we calculated the result. We got nonlinearity hysteresis less than 0.3% of full scale output, and sensitivity is around zero point 0.3 for 20 bar and zero point 0.1 for 40 bar, and full scale output around 30 millivolt for 20 bar, and for both the sensor we got around 30 millivolt for full scale output, and zero offset as you can see here. The conclusion, we successfully completed the graphene nanocomposite based resistive strain gauge design, development, fabrication, even assembled, integrated and tested. So we calculate the all the calculation using the proper method, and we got a very good satisfactory result also. And we are getting less after repeating few times, the we are getting the less nonlinearity hysteresis around 0.34 of full scale output. So after repeating so many time, we got a good repeatability result, stability, and fast response, a low hysteresis, and main thing is in our device is low cost, because without any using the clean room facility or other things, we can make it out, and even we can make the trailer made method also. So these are my reference and some of the uh, papers we published and presented in the conference. Thank you, everyone.
Thank you, Pavitra. That's great work. And we congratulate you once again for this work.
Thank you, ma'am.
So we'll go ahead with the next presentation. The next set of awards is UG, is from the UG category. We have the winner for the ISSS UG Student Award for the year 2020. It's been awarded to Ms. Kirtana Ji, Mr. Anirudh, and Mr. Kunal of Nitte Meenakshi Institute of Technology for their work on design, fabrication, and characterization of quantum dot-based humidity sensor. And they have carried out this work under the supervision of Dr. Habibuddin Sheikh. ISSS congratulates the entire team, and now I request the awardees to share the screen and present their work. Who will be presenting, sharing the screen?
Yeah, good afternoon and all.
We cannot see your presentation.
Just 1 minute, madam.
Yeah, now you can. Make it full screen. Yes, go ahead.
Good afternoon and all. Firstly, I would like to thank the selection committee and ISSS for selecting our team and giving us a chance to project our work. I am Kunal and my team consists of Anirudh and Kirtina. We'll be presenting a project titled Design, Fabrication and Characterization of Graphene Quantum Dots Based Humidity Sensor. Carried out under the guidance of Dr. Habib, our project deals with the synthesis of graphene quantum dots and its use as a sensing material in humidity sensor. Graphene quantum dots have drawn significant attention in the past few years. GQD is porous, electrically and chemically stable, biocompatible, and highly sensitive. These features make GQD a desirable material in the sensing field. The reason for its high sensitivity is a phenomenon called multiple exciton generation, which involves the generation of more than few tens of exciton in the conduction band from the absorption of a single photon. GQDs were synthesized via carbonization of citric acid. 2 grams of citric acid was taken in a test tube, and the test tube was subjected to heat through heater belt. So the temperature rise to 200 degrees Celsius gradually. After 23 minutes, the test tube was removed and color of the samples were observed. The same process was repeated for 9 other samples with an increment of 2 minutes between each sample. From these pictures, it is evident that longer the citric acid sample was heated, darker is the color. This is because an excited electron cannot remain in the high energy state and jump back to the valence band, releasing energy in the form of light whose wavelength depends on the energy gap. Therefore, larger the dot, lesser is the energy gap, and longer is the wavelength of light. The prepared samples were characterized using Raman spectroscopy and XRD. In Raman spectroscopy, it was observed that the results do not have characteristic peak. As the fluorescence spectrum of the precursor dominated the Raman peaks of GQD. Therefore, the results gave no conclusive evidence of the formation of GQD. However, the results obtained after XRD confirmed the presence of GQDs. The signature peaks of graphene oxide was observed around 9 degree, and the samples whose XRD outputs did not have graphene oxide peaks were selected. The GQD samples heated for 33 minutes was chosen to be the ideal sample, and to broaden our spectrum, sample heated for 31, 35, and 37 minutes were also considered for testing. These GQD samples were divided into 3 portions, and the pH of each portion was adjusted to 5, 7, and 9 respectively by adding 0.1 molar NaOH in suitable quantity. For the sensor fabrication, interdigitated aluminum electrodes with the shown dimension were deposited on glass substrate by thermal evaporation. Probes were drawn, and a small amount of graphene quantum dot solution was pipetted on the interdigitated electrodes to prepare the humidity sensor. The sensor was tested under varying relative humidity conditions using an electrochemical analyzer. The voltage current characteristics of the sensor was analyzed, and the study was carried out on the sensor without and with GQD. A constant voltage of 1 volt was applied between the electrodes and the current was measured. On varying the humidity, the sensor without GQD solution showed a 2-order change in the current as shown in the figure, whereas there was a 6-order change in the current for a sensor with GQD. It is also evident from the figure that the response time is also less for the sensor with GQD. In summary, it was found that GQD can be used for humidity sensing. Furthermore, GQD can be easily synthesized in laboratory level. The results obtained showed the sensitivity is greater and response time is shorter with GQD solution. This was confirmed from the VI characteristics of the sensor, and for the sensor to be practically useful, other physical and chemical properties need to be characterized. As a scope of future study, the sensor are to be tested under controlled conditions with variety of GQD samples along with variation in pHD to validate its practical use. Electrodes can be deposited using different metals such as platinum and gold for comparing the responsivity. Thank you for giving me this opportunity to present our work. Thank you.
Thank you, Kunal. It's really a great work that was presented, and we wish you all the best. Can you stop sharing? We'll be going ahead with the next award. So the ISSS first runner-up under the ISSS UG category goes to Mr. Swaroop, Mr. Kailash, Mr. Amrit, and Mr. Chandrasekhar of Nitte Meenakshi Institute of Technology for their work on simulation, fabrication, and characterization of zinc oxide planar TFT. They have carried out this work under the supervision of Dr. Habibuddin Sheikh. ISSS congratulates the entire team for this effort and this work. And now I hand over the platform for the entire team. So please share the screen and present your work. Are you presenting, Chandrasekhar?
Ma'am, Swaroop will be presenting, ma'am.
Okay, please share the screen then. Yes, make it full screen. Please go ahead.
Good afternoon to one and all present here. Myself, Chandrasekhar, and my team consists of Amrut, Swaroop, and Kailash. Today, we are here to present project titled Simulation, Fabrication, and Characterization of Zinc Oxide Planar Thin Film Transistor, which was carried out under the guidance of Dr. Habibuddin Sheikh. We would like to extend our gratitude to the ISSS jury panel for selecting our project. Next slide. Moving with the objective of the title project is to simulate the device and get the characteristics using Silvaco TCAD, followed by SEM and XRD characterization, then to fabricate a backgate non-silicon based planar thin film transistor and obtain input-output characteristics. Moving with the device dimensions, device 1 dimensions. Next slide. Moving with device 1 dimensions, gate of aluminium 300 nanometer thick and gate oxide of aluminium oxide 20 nanometer thick was deposited using electron beam evaporation technique, followed by zinc oxide of 5 nanometer, which was deposited using RF sputtering. Finally, source and drain terminals of aluminium of 200 nanometer thick was deposited using electron beam evaporation technique. Next is the simulation results of the device mentioned previously. It is evident that from input characteristics, the threshold voltage of the device was found to be 0.69 volts for a constant drain to source voltage of 0.55 volts. From the output characteristics, it is evident that the characteristic curve tends towards saturation region with a constant increase in gate to source voltage. Moving on with the next slide, we have input-output characteristics of the device, which was achieved through EC Lab software. Using input characteristics, it is evident that The threshold voltage of the device was found to be 0.69 volts with a constant drain voltage of 0.55 volts. From output characteristics, uh, the VI characteristics aren't smooth enough and there are disturbance in the curve. This is because of ultra low thickness of channel and oxide layer with increasing leakage current. Further, my teammate Swaroop will lead the presentation ahead.
Good afternoon, all. So, to address this drawback, we designed a new device with increased gate oxide and channel layer thickness as shown. After the simulation, threshold voltage was found to be minus 9.56 volts. So, moving on. Before the fabrication of actual TFT, 3 samples of aluminum oxide and zinc oxide were deposited using DC reactive sputtering method with a different target power and a different oxygen partial pressure respectively. So SEM and EDS analysis was done for the samples of aluminum oxide. One of the things that we can infer from that is if we set the target power slightly higher than 65.5 watts, we will get aluminum oxide with the proper stoichiometric ratio. So moving on, the XRD analysis was done for both aluminum oxide and zinc oxide samples. From the figure below, we can infer that zinc oxide is polycrystalline in nature due to a characteristic peak which is formed at 34 degrees. So now we move to the deposition of the TFT. These are the optimized deposition parameters used in the deposition of aluminum oxide and zinc oxide channel layer. Aluminum oxide was deposited with target power of 81.22 watts and with deposition rate of 5.833 nanometer per minute. And zinc oxide was deposited with target power of 77.5 watt and deposition rate of 20 nanometer per minute. We can calculate the thickness as shown in the last row. So moving on, this slide shows the dimensions of the second device, device 2. Gate layer is made of aluminum and has a thickness of 300 nanometer. Gate oxide layer has a thickness of 175 nanometer. And channel layer has a thickness of 200 nanometer. And the source drain is made of aluminum. It is deposited during thermal evaporation. So the input and output characteristic of the second device is shown. The threshold voltage is minus 9.5 volts for VDS of 10, constant VDS of 10 volts. Both input and output characteristics are match the simulated results. As we can see, there is also minimum disturbance than.
Sarup, you have 2 minutes.
Right. Yeah, yes, ma'am. So these are the references. So we also thank the Sense department at ISSC for providing SEM and XRD support. Thank you.
Thank you, Sarup. That's indeed a great work, and we wish the entire team the very best for carrying out their future endeavors. We congratulate you once again.
Thank you.
Can you stop sharing, Sarup? Thank you. So we go to the last in our list of presentation, and so the second runner-up in ISSS UG Student Award category goes to Mr. Ashutosh Singh, Mr. Akhil Ranjan, Mr. Manish Kumar Singh, and Mr. Nikhil of Nitya Meenakshi Institute of Technology, Bangalore, for their work on IoT-based water quality analysis and purification system. They have carried out this work under the supervision of Professor Nitya G. ISSS congratulates the entire team for this work, and I request now the team to share the screen and make their presentation.
Hello everyone, Ashutosh here. Thank you for. I will just present the screen 1 second. Are you able to see the screen?
It's coming up. Wait, yeah, you can make it in full screen. Yes, please go ahead.
Hmm. Hello everyone, good afternoon. Thank you for to the ISSS jury on the behalf of my team for this consideration. We as a team are humbled for this consideration. I would also like to thank our professor, Dr. Nitya ji, for her constant support and guidance. So our project was based upon IoT-based water quality analysis and purification system. So about the project. In this venture, we have tried to present and design and develop a low-cost, fully automated system for measuring the water quality, along with an integrated three-stage purification system with the use of the IoT power. And so this is our project has mainly two parts. The first part is as a measurement kit, and the second stage is the purification system. In the measurement kit, what we try to do is like we have embedded several sensors: dissolved oxygen sensor, temperature sensor, turbidity sensor, pH sensor, conductivity sensor, and have tried to reduce the quality of the water, like what is the content of, what is the solvent, how much is the turbidity of the water, how much is the dissolved oxygen content, so we can find out how much the water is pure, and based upon that we can make the further conclusions and do more work. So this was the measurement kit we designed. As you can see, this is the pH, this is the turbidity sensor, this is the temperature sensor, this was the dissolved oxygen sensor. So we have and going on to the next step. So this is the purification system. Our purification system is based on three stages: primary stage, secondary stage, and tertiary stage. So what we try to do is we try to take different types of water, whether be a sewage water, normal household water, and first we measure up what is the quality of the water, and then we try to improve it. And in a way, it is like a real-time water quality measurement and the purification system. So in the primary stage, what we do is like we collect the water in a receiving chamber, then we try to remove the bigger particles, and then after we try to remove all the oil and grease components, and put up the sediment in a disposable tank and take the remaining purified water to the secondary stage. In secondary stage, the secondary stage is mainly of the chemical things, where we try to aerate the water and increase the dissolved oxygen content of the water, because dissolved oxygen content is the primary factor which supports the life. The greater is the dissolved oxygen content, the greater it sustains life for the aquatic animals, as well as it becomes more pure for drinking. So after the aeration, we try to add the PAC addition to observe all the dust and the colloidal particles, and then we at the same time we are also measuring the quality, like how much the quality is increasing, how much this DO has increased, the temperature, the pH of the acidity, base, alkalinity as well. And at the third stage, what we do is like we try to make the water drinkable to drink for the human consumptions. So in the tertiary, we have implemented several cartridges like the multi-grade filters, then the UF vessel, RO vessel, and the UV vessel with a TDS controller. So we try to make the water potable for drinking. So we have also, this is the whole block level diagram of what we have tried to done. Like we have all embedded the cloud, so that we can receive the real time data on our mobile system, and we can control the whole system. So this was the purification system which we tried to design. This was the primary screening chamber in the primary stage. This was the secondary stage in which we try to increase the DO content of the water, and this is the PAC cartilage with along with several other cartilages. And this was the UI which we developed for getting the real-time results, which means the pH, DO, turbidity, and then the see the how the color of the water as well. And here we also try to control our purification system by turning on the screening chamber, then the secondary stage as well as the tertiary stage. At the last, we also tried to do a performance evaluation, like how much our system has been designed and is correct. So we tried to compare it with the chemical approach. A separate team in the NMIT did the observation using the chemical approach, and we tried to did this same observation with our developed sensors. So what we did, like the chemical people find out the turbidity, pH, the DU content, and the temperature, as well as our measurement kit find out all those things. So we got more than a 90% accuracy with this result. So, and also we measured the water samples at different temperatures to find out the DO contents, like how the DO content decreases as the temperature of the water increases. So that's all of our project. Thank you, everyone.
Thank you, Ashutosh. It's a great work and all the best for your future and congratulations once again.
Yeah.
Now, I would request Professor Atre, if you can speak a few words. Atre sir, are you there?
Hello, can you hear me?
Yes, sir, we can.
Yeah, my congratulations to all the winners of the award. Keep going, and just remember that the papers you publish should also be given a chance in the Indian journals, and if you can select ISSS journal, it will be good. However, you must also realize that I quite happy to see that most of them are application-oriented and device-oriented research in India. I think finally we are probably shifting towards technology development, and the next decade or so with the attitude of the present government probably is a very important issue, and such kind of a thing is always good. 25 years back, I first started talking about MEMS and positive these really 25 years now, and some of the things which probably Anand Suresh will be aware of. We talked about flexible electronics and what kind of biomedical chips are coming to do. And some of the presentations were outstanding, and I hope you continue in the present form. These awards is just to encourage you, saying that your work has been recognized by a peer group. And that's what you have done. And I hope you keep doing it. And even when you go away to work in industry or academic institutions, just keep remembering that the innovation is very important, and you're going to be continuously looking at the innovations in to come. And I'm glad that this has been arranged. And again, congratulations to all of you. Thank you.
Thank you, sir. Anand Suresh sir, you would say a few words?
Oh, I thank all the people who attended this event, and also the speakers for taking the time to present. And I wish you all very best in your careers. Thanks, Veda, for organizing this along with Sunil and Dev.
Yeah, thank you. Thank you one and all for attending, and once again, congratulations. And your certificates and cash awards will reach you very shortly. And try to become ISSS members if you're not already, and try to spread awareness of ISSS in your community and peer groups. That will help ISSS and help many others to get the platform that you all have got today. Thank you. Thank you all.
Thank you. Bye.
Bye.
Good night to all.